If you take a solid block of aerospace-grade titanium and you try to cut it with, the thickest, toughest metal blade on Earth, you actually won't break the titanium.
No, definitely not.
You will literally melt your own tool. Think about that for a second. We're so conditioned to view metalworking as this ultimate act of brute force.
Right. Like sparks flying everywhere, massive drop forges slamming down.
Exactly. Just violent collisions of iron and steel.
Yeah.
But modern manufacturing just doesn't work that way.
Not at all. I mean, it's a very primal image, right? Man versus iron. But it's a complete illusion. On a modern, high-tech factory floor, if you just try to bully these advanced materials by, pushing harder, they will destroy your equipment in a matter of minutes.
And if you've ever looked at a jet engine turbine, or, I don't know, even just the surgical grade steel of a watch on your wrist, you're looking at metals that actively fight back when you try to shape them.
Oh, absolutely. They do not want to be cut.
Right. And today's deep dive is tailored specifically to show you exactly how engineers win that fight. Our source material today comes directly from ISCAR's technical guides on precision geometries for machining difficult materials.
It's a fascinating set of guides.
It really is. And our mission today is to uncover the hidden physics of manufacturing. We are exploring why the microscopic 3D shape of a cutting tool matters, infinitely more than just the raw toughness of the metal it's actually made from.
Which is such a massive paradigm shift for a lot of people.
Okay, let's unpack this. Why do these incredibly difficult to cut materials demand such insanely specific microscopic geometries?
Well, to really understand the why, we have to zoom way, way in. Forget the huge machine itself for a second.
Yeah, zooming in.
Picture the microscopic battlefield right where the cutting tool actually meets the metal. The ISCAR sources lay out a very specific set of hostile traits that these advanced materials share.
Hostile is a good word for it.
Yeah, because they maintain high strength, even when they are red hot. They are incredibly abrasive, and they have horrible thermal conductivity.
Meaning they basically don't let heat escape.
Right, exactly. Plus, they have these bizarre defense mechanisms like work hardening, which we will definitely dig into in a bit, and they tend to form these long, unbroken, razor-sharp ribbons of metal when you try to slice them.
So you're facing an enemy with that exact profile. ISCAR's guides make it really clear that the tool's insert geometry, the literal 3D shape and angle of the cutting edge, is your master control switch.
It dictates everything.
Right. The cutting forces, where the heat goes, how the metal chips break, whether the part actually survives. The goal is striking this impossibly precise physical balance.
Yeah, but that balance completely shifts depending on the specific metal. You cannot use a one-size-fits-all approach here, relying solely on, say, throwing a really tough, expensive carbide material at the problem without engineering the geometry.
Let me guess. Guaranteed failure.
Guaranteed failure. You'll just break expensive tools.
Now, I have to play devil's advocate for our own human intuition here. Because if a metal is incredibly hard and abrasive and tough, my brain immediately says, use the bluntest, thickest, most heavily reinforced tool possible.
Which is a totally normal way to think about it.
Like, if I have a piece of dense, aged Parmesan cheese, I don't use a flimsy, razor-thin blade, I use a thick wedge to crack it open. Shouldn't a thicker, blunter tool just overpower the hard metal through sheer force?
What's fascinating here is exactly how that brute force intuition just completely falls apart under the laws of physics.
Really?
Yeah. Let's look at what's actually happening at the atomic level. When you cut metal, you aren't just splitting it like wood. You are forcing the metal to shear along a plane. You're physically breaking its molecular bonds.
Okay, I'm with you.
So if you take a blunt, thick wedge to a high-strength metal, you aren't cleanly shearing it. You are essentially just rubbing against it at hundreds of feet per minute.
And rubbing means friction.
Exactly. Massive amounts of friction. And friction creates heat. In machining, uncontrolled heat is the ultimate enemy. A blunt tool generates so much heat that you actually ruin the cutting action.
Because it melts.
Basically, yeah. You destroy the metallurgical integrity of the part itself. You might warp it or change its temper, and you physically melt or shatter the cutting tool. You don't overpower the metal, you just cook your own equipment.
Oh, wow. Which perfectly brings us to the exact materials where heat isn't just a byproduct. It is the central defining crisis of the whole operation. I'm talking about titanium and heat-resistant superalloys, or HRSA.
Right, the aerospace stuff.
Exactly. You see these heavily in aerospace. They are incredibly strong, and they handle extreme temperatures beautifully when they're, flying at 30,000 feet. But that exact same property makes them an absolute nightmare to manufacture on the ground.
Precisely, and it goes back to that poor thermal conductivity we mentioned earlier. Think about cutting a standard piece of steel. A lot of the heat generated by the friction of the cut travels into the metal chip that's peeling away.
So the chip takes the heat with it.
Yeah, some travels into the tool, some dissipates into the larger part itself. It shares the thermal load. But titanium and superalloys act like thermal insulators. They aggressively trap the extreme heat right at the cutting zone.
So the tool is basically just sitting there baking in its own friction.
Baking, it's just absorbing all that destructive energy.
Here's where it gets really interesting. Because to solve this trapped heat crisis, ISCAR goes completely against that blunt force intuition I just argued for. To cut these tough aerospace metals, the solution is actually high positive rake geometries.
Which sounds technical, but it just means do.
Yeah, in non-machinist terms, they use an incredibly thin, razor-sharp edge.
It sounds totally counterintuitive, right?
Yeah.
To use a delicate, sharp edge against something as tough as titanium. But let's visualize what a positive rake actually means. Think of a snowplow blade driving down a highway.
Yeah, I got a snowplow in my head.
If the plow is perfectly straight up and down, like a wall, it takes a massive amount of engine power to push the snow. And it creates huge resistance. But if you tilt the top of that plow blade far back, giving it a positive angle, the snow slides up and over the blade smoothly with very little resistance.
Ah, so that tilted back snowplow is a positive rake angle.
Exactly. By using a highly positive rake geometry on the cutting tool, you create a very narrow, sharp contact area. This razor-sharp edge slices cleanly under the titanium rather than pushing or rubbing against it.
So you're avoiding that rubbing friction.
Exactly. That clean shear dramatically reduces the friction, which lowers the power consumption and, most importantly, stops the heat from building up in the first place.
And essentially turns the metal chip into a heat escape vehicle. The sharp edge slices so cleanly that the chip flows smoothly up and away from that tilted snowplow face, physically carrying the heat away before it can soak into the tool.
That's the exact mechanism.
And ISCAR has engineered some very specific geometries to execute this.
The Heeley turn is a great example of this physics in action. Heeley stands for helical. Instead of a flat, straight, cutting edge slapping into the metal all at once, the edge is twisted.
Twisted, like a drill bit.
Think more like the blade on a real lawnmower. It enters the metal gradually, which significantly lowers the radial cutting forces and reduces the shock to that sharp, delicate edge.
That makes total sense. The guides also point to the logic 6-turn inserts, specifically the M3M and F3M geometries. These give you multiple extremely sharp cutting edges on a single insert.
Right, with optimized shapes to control how that chip flows.
And ISCAR pairs these razor-sharp physical shapes with specific chemical coatings. Grades like IC806 or IC907, which are formulated to act as a heat shield against the high-temperature chemical reactions that happen when cutting superalloys.
There is another massive variable with titanium that this sharp geometry helps solve, by the way: vibration.
Oh, because it's bouncy.
Yeah, because titanium is so strong, but also somewhat elastic, it tends to be very bouncy during a cut. It creates chatter. Chatter is a rapid, violent vibration that sounds like a screaming banshee and completely ruins the surface finish of the part.
And obviously, if you have a razor-thin, delicate, positive rake edge, violent vibration is going to snap it instantly.
Instantly. It'll just shatter.
So to combat this, the sources note that ISCAR uses whisper line turning tools. These tool holders have dampening mechanisms built inside them to literally absorb and suppress that chatter. It stabilizes the razor-sharp geometry so it can cleanly slice without vibrating itself to pieces.
So for titanium, extreme sharpness and smooth flow are how you banish the heat. But the entire playbook gets thrown out the window when we look at a different class of difficult material.
Stainless steel.
Exactly. While titanium destroys tools with trapped heat, stainless steel employs a dynamic, physical defense mechanism. It actively fights back against the tool.
Wait, I'm stuck on something before we get to that. We just established that heat is the ultimate enemy, and we use a razor-sharp tool to slice cleanly and avoid friction. Wouldn't we want to use that exact same razor-sharp tool on stainless steel to keep it cool? Why are we intentionally compromising?
That is exactly where the physics throw us a curveball. The problem with stainless steel isn't just heat. It's a phenomenon called work hardening.
Okay, let's explore this work hardening trap, because this genuinely blew my mind when I was reading the sources. When you try to cut stainless steel, the physical pressure of the cutting tool actually compresses the atomic lattice of the metal right in front of the cut.
Yeah.
You are literally packing the atoms tighter together, forging a hardened layer of armor just by trying to slice it.
It's incredible. The more pressure you apply or the more you rub against stainless steel, the harder the surface gets. If your tool hesitates for even a microsecond or just doesn't cut decisively, it ends up gliding over this newly formed, hyper-hardened surface.
So that delicate, highly positive razor edge from our titanium toolkit would just instantly snap against that armored layer.
Precisely. We need a geometry that is sharp enough to bite underneath that work-hardened layer before it fully forms, but structurally thick enough to survive the impact. So ISCAR shifts away from high positive rakes to what they call medium positive rake geometries.
So the snowplow is still tilted back, but not nearly as far.
Exactly. The edge has a lot more meat behind it.
But work hardening isn't even the most dramatic problem with stainless steel, is it? The real nightmare is the chips. Because stainless is incredibly ductile, meaning it stretches rather than breaking, it produces long, continuous, stringy metal chips.
They are awful to deal with.
Instead of snapping off into neat little pieces, the metal peels off like an endless razor-sharp metallic ribbon.
And that ribbon doesn't just fall away, it spirals. It wraps around the spinning tool, it wraps around the part, it tangles in the machine. It is incredibly dangerous.
So what is the geometric solution? This is where the true heroes of the ISCAR inserts come in. The chip breakers. We mentioned the logic turn MF and MM geometries earlier. The M stands for medium machining, the F for finishing. But the magic isn't just the edge.
Right, it's what's modeled directly behind the edge. A chip breaker isn't some separate moving part. It is a microscopic 3D topography engineered directly into the top surface of the cutting insert. Think of it like a microscopic skateboard park sitting right behind the cutting edge.
I love that visual. A microscopic skate park.
Yeah. When that stringy stainless steel ribbon peels off the main edge, it hits this specific 3D ramp. It is violently forced to travel up the ramp and curl back on itself into a tight circle.
So it folds it over.
The geometry forces the ribbon to curl so tightly that the physical tension exceeds the strength of the metal, and it loudly snaps into a small, harmless shape, like a little metal C or a 6.
If we connect this to the bigger picture, this chip control is staggering in its importance. This isn't just about keeping the factory floor neat. It is a critical million-dollar productivity issue. A tangled mass of sharp, work-hardened stainless steel chips, what machinists call a bird's nest, can wrap around the chuck, score the freshly cut part, rip the cutting tool right out of its holder.
Oh, it can completely halt a production line. Exactly. Imagine a lights-out manufacturing facility. You have robots loading parts into machines overnight with zero human supervision.
Just totally automated.
Right. If one single stringy chip fails to break and wraps around the tool, it shuts down the entire multi-million-dollar operation until morning. The exact 3D slope of that tiny microscopic skate park, that chip breaker, is literally the linchpin holding the entire automated factory together.
It is wild that all that automation rests on the shoulders of a tiny groove on a piece of carbide. Okay, so we've used razor-sharp finesse for titanium, and we've used medium-sharp, chip-breaking brute force for stainless steel. But what happens when we face materials that are already at their absolute maximum hardness before we even start cutting?
Like hardened steels or highly abrasive cast irons.
Exactly. What do we do then?
In that scenario, the physics flip completely again. When you are machining hardened steel, edge, strength, and stability become your only concerns. You are no longer trying to whisk away heat with a delicate slice, and you aren't trying to curl a ductile chip.
You're just trying to survive.
You are trying to survive an incredibly violent high-pressure collision. If you used our tilted snowplow edge, it would suffer from massive edge collapse. It would literally shatter like glass.
So the guides specify that ISCAR undertakes a total structural shift. They move to moderately positive or even completely neutral rake angles.
To go back to our analogies, if a positive rake is a tilted snowplow, a neutral rake is a bulldozer blade standing straight up. It meets the metal head-on. Or, better yet, think about walking on a frozen lake.
Okay, frozen lake.
If you walk on thin ice in stilettos, you punch right through because all your body weight is concentrated on a tiny, sharp point. But if you wear snowshoes, you distribute that exact same weight over a wide, flat area, and the ice holds.
That makes perfect sense. A neutral rake angle acts like a snowshoe for the cutting edge. It spreads out the massive collision forces of the hard metal so the tool doesn't shatter. And ISCAR reinforces that edge even further with specific microgeometries, like honing and chamfering.
Right. Honing is essentially taking that sharp tip and microscopically rounding it off so there's no fragile microscopic point to chip.
And chamfering.
Chamfering goes a step further by adding a tiny flat bevel, like a micro ramp, right at the leading edge to give it maximum structural support. It's blunt, but precisely blunt. ISCAR utilizes their robust logic turn RM geometries for this, combining them with heavily reinforced insert grades.
And what this combination of snowshoe geometry and chamfering enables is a process called hard turning. I really want to emphasize what a massive paradigm shift hard turning is in manufacturing. Historically, if you had a piece of steel that was already heat-treated and fully hardened, say, a gear shaft for a transmission, you couldn't put it on a lathe and cut it with a tool. It was too hard.
No, you had to use a grinding wheel.
Exactly. And a grinding wheel is essentially just a spinning rock that slowly sands the metal away, spark by spark. It is an incredibly slow, meticulous, expensive, and messy process. But with these newly engineered neutral rape geometries, you can take a cutting insert and literally carve that fully hardened steel on a standard lathe.
It's amazing to see.
It's like taking a process that used to require hours of slow, delicate sanding and replacing it with a bulldozer blade, so perfectly engineered that it can violently shear away solid granite without breaking a sweat. It massively boosts productivity.
It's a total revolution in throughput. Manufacturers can often skip the grinding machines entirely. But it is only possible because the exact geometry of the tool, that neutral rake and chamfered edge, has been perfectly calculated to withstand those astronomical pressures.
Speaking of astronomical pressures, slicing along the outside surface of a spinning metal cylinder is one thing. But the ISCAR sources take us into an even more extreme stress test: grooving and parting operations.
Oh yeah, that's a whole different beast.
This is when the tool isn't just skimming the surface. It is plunging directly into the meat of the material, cutting a deep trench or slicing the part completely in half.
In grooving and parting, you face what we call full-width engagement. The metal is squeezing the tool from the top, the bottom, the left, and the right simultaneously. And worse, the chip has nowhere to go.
Right, because it's in a trench.
Exactly. It can't fly off to the side. It has to travel straight back out through the narrow channel you are actively cutting. The friction and stress are immense.
ISCAR addresses this full-width squeeze with their cut grip system. This system offers dedicated geometries, specifically their F, M, and R geometries, that are completely optimized for plunging into different materials. Because you are cutting a narrow groove, the inserts themselves have to be very thin.
But they also have to maintain incredibly high rigidity so they don't snap under that side-to-side squeezing pressure.
And the chip evacuation has to be absolutely flawless here. If a stainless steel chip gets jammed in that narrow groove, it welds itself to the part and the tool explodes instantly.
Instantly. It's a catastrophic failure.
Right. But this raises an important question, something we haven't even touched on yet. We've talked about all these specific geometries, the helical twisted edges, the microscopic skate parks for chip breaking, the neutral snowshoe edges. How do manufacturers avoid getting completely overwhelmed by all these variables? Because we haven't even talked about the machine pushing the tool yet.
This raises an important question, absolutely. It is a massive matrix of variables. The insert geometry doesn't exist in a vacuum. The final choice is dictated by the type of operation, how deep you are cutting, how fast you are feeding the tool into the metal, and crucially, the physical stability of the machine tool itself.
Right. If you have a lighter, less rigid machine that might vibrate or flex a little bit under pressure, the ISCAR guides say you actually need to use more positive, sharper geometries to keep the cutting forces low.
Otherwise, you'll stall the machine's motor.
But if you have a massive, heavy-duty, highly rigid machine taking deep cuts, you demand those stronger, blockier edges. Oh, and high-pressure coolant. Blasting coolant directly into the cutting zone further alters the equation, enhancing chip control and tool life even more.
It's an incredibly complex equation. But manufacturers manage this overwhelm because companies like ISCAR engineer these application-specific geometries to operate within strictly defined cutting windows.
Cutting windows.
Yeah, they map out exactly what feed rates, speeds, and depths a specific geometry can handle. As long as the operator stays within that defined window, the microscopic geometry does all the heavy lifting. It delivers predictable, repeatable results regardless of the specific machine setup.
It really is a symphony of variables. So what does this all mean? We started out talking about the illusion of brute force in metalworking. But by looking closely at these ISCAR technical guides, we've uncovered an incredible hidden world.
We really have.
We've seen how machining difficult materials isn't about violently smashing metal against metal. It is a delicate, perfectly calculated dance. From the razor-sharp, heat-evacuating positive rakes that carefully slice through aerospace titanium, to the microscopic skate parks taming the work-hardening traps of stainless steel.
All the way to the robust, heavily reinforced snowshoe edges capable of shearing fully hardened steel.
It is geometry, metallurgy, and physics tailored to the unique personality of every single metal.
If we connect this to the bigger picture, it's a brilliant reminder that true engineering mastery isn't found in overwhelming force. It's found in deeply understanding the constraints of your material and designing the perfect, precise, physical mechanism to overcome them.
I love that. And I will leave you with a final thought to mull over. Take a second and think about the physical objects around you right now. Maybe it's the sleek metal casing of your smartphone, the high-performance components inside your car's engine, or, even just the heavy-duty hinges holding up your door.
They're everywhere.
They really are. The next time you look at a perfectly machined metal component, don't just see the finished product. Ask yourself, what invisible geometry, what perfectly calculated microscopic angle, and what hidden physics had to be engineered just so that one stubborn piece of metal could be shaped into reality? Thanks for joining us on this deep dive.